Solution of 23 Unit 2 Advanced Mechanics Semester 6 Mathematics Honors University of Calcutta. Welcome dear students. This is the question paper 2023. This is Unit 1 Unit 2 Question 3a Part 1. A particle in 2 dimensions is in a potential V functions of xy equal to x plus 2y. Write down the expressions for the canonical momentum px and py. Hence, so that py minus 2px is a constant of motion. In part 2 question, the Hamiltonian of a dynamical system of 2 degrees of freedom is given by h equal to this, where a and b are constants, so that f1 equal to p1 minus aq1 whole divided by q2 is a constant of motion. First part, question 3a. For two-dimensional motion, kinetic energy T equal to half in x dot square plus y dot square. For a particle at the point Pxy of mass m at any instant t, and potential energy V equal to x plus 2y, and it is given the question Px equal to this. Then the Lagrangian L of the system, this equal to t minus v, this equal to half in x dot square plus y dot square minus x minus 2y. Equation 3. Let px and py is a respective canonical momenta of x and y, then px equal to del x dot L and py equal to del y dot L. Equation 4. Also, the Lagrange's equation of motion ddt of del x dot L minus del x L equal to 0, and ddt of del y dot L minus del y L equal to 0. Hence, this value of del x dot is equal to px, and this del y dot equal to py by 4. So px dot equal to del x L and py dot equal to del y L. Now find del x dot equal to mx dot and del y dot equal to my dot, because L is this expression 3 half mx dot square plus y dot square minus x minus 2y. So obviously this del x L equal to minus 1, del y equal to L, and hence px equals to del x, so mx dot and py equal to my dot, and these are the required expressions for px and py. PHEAC, and px dot equal to minus 1 and this py dot equal to minus 2, equation 6, because px dot equal to del x, so del x equal to minus 1 and this minus 2. Now ddt of py minus 2px, so this py dot minus 2px dot, and the value of py dot and px dot equal to minus 2 and minus 1, so this equal to 0, hence py minus 2px is a constant, and so the py minus 2px is a constant of motion. Next question, part 2. Hamiltonian canonical equation of motion is given by qi dot equal to del pih and pi dot equal to minus del py h, I equal to 1, 2. H equal to q1 p1 plus minus q2 p2 minus a q1 square plus b q2 square. This is equation 1. And q1 dot equal to del h del p1. So this with respect to q1, so here q1, and q dot equal to del h del p2. So this minus q2, equation 2. p1 dot equal to minus del q1h. So with respect to q1, so this p1 minus, so this minus p1 plus 2a q1. p2 dot equal to minus del q2h, which is equal to p2 minus 2b q2 from 1. And this part is extra, so avoid this part within third brackets. So up to this portion is the extra portion, and actually we find here P1 and P2, values of P1 and P2. Now in the given question, we have to find this P1 minus a Q1, Q2 is a constant of motion. So dt of this and the value of P1, Q1, and this from P1. This is the derivative. So and denominator square, denominator into numerator derivative minus numerator into denominator derivative. So we have get this Q2 P1 dot and so on this, and taking common Q2 by Q2 square. So P1 dot minus AQ1 dot plus P1 minus AQ1, and after simplification we get 0, and hence this is the P1 minus AQ1 by the Q2 is a constant of motion. This portion is a constant of motion. Next question, question 3b. A particle with coordinate q and momenta p has the Hamiltonian h qp square minus qp plus bp, where b is a constant. Solve for p and q. The Hamiltonian canonical equations of motions give q dot equal to del del p h. So with respect with respect to p, so we get this equation 1, and p dot equal to minus del del qh, so we get this minus p square plus p equation 2. From 2 we get ddtp equal to p minus p square. So after separation of derivative we get dp by p minus p square equal to dt, and this partial fraction 1 by p minus 1 by p minus 1 dp equal to dt, and integrating this log to the base e by p minus 1 plus p plus c is a constant of integration. Hence after simplification we get this 1 by p equal to 1 minus 1 by p to the power p plus c, and hence p equal to this, and this equal to half of bracket 1 plus hyperbolic cot p plus c by 2. Actually hyperbolic cos equal to e to the power x minus e to the power minus x by 2, hyperbolic sine x equal to e to the power x minus e to the power minus x by 2, and so cot hyperbolic x equals to cos hyperbolic x by sine hyperbolic x, this equal to e to the power x minus e to the power x minus x by e to the power x minus e to the power minus x, and after simplification we get this. So we get 1 plus cot hyperbolic p plus c by 2, and from 1 this is the 1 q dot equal to 2p minus 1 bracket q plus b, and from 1 we get ddtq equal to q hyperbolic cot t plus c by 2 plus b, and dq dt minus q hyperbolic cot t plus c by 2 equal to b. This is a linear equation in q. So we get the formula q into e to the power minus integral this pdx for hyperbolic dt here equal to b into integration e to the power minus e to the power pdx into dx plus c here dt. So q this e to the power this, so this is the cosec hyperbolic square t plus c by 2. This because integration hyperbolic cot t plus c by 2 equal to 2 hyperbolic integration cot hyperbolic z dz. If we put t plus c by 2 equal to z, and so changing the variable, this 2 log modulus of sine hyperbolic z is equal to log of sine hyperbolic z square. So we get cosec hyperbolic square t plus c by 2, and this is equal to b integration cosec hyperbolic square t plus c by 2 dt plus c dash is constant of integration, and after integrating we get minus 2b cot hyperbolic t plus c by 2 plus c dash. So q equal to c dash hyperbolic sine hyperbolic square t plus c by 2 minus twice b hyperbolic cos t plus c by 2 into cos sine hyperbolic t plus c by 2 equation 4. Thus the expression 3 and 4, this 4 give the solution of the dynamical problem. This 4, and we get q, and from 3 we get the value expression for p. Next question 3C. A particle of mass m is attracted towards a given point by a central force of the form k by r square, where k is constant. Assuming that the central force is conservative in nature, write down the expression for the Hamiltonian of the system and derive Hamilton's equation of motion. Here attractive force, so this F equal to minus k by r square, k is a positive constant, and this force F this equal to grad V, this equal to minus actually here scalar value of this. So magnitude of F, so minus del RP equal to minus k r square. Actually, this is the component of this minus k by r square. This is the potential energy. And so V equal to integration infinity to R k by R square. Actually, this is equal to minus k by R in R infinity to R, so minus k by R. Actually, this minus cancel here. This function, so minus k by R. Here R and theta are generalized coordinates. These generalized coordinates. So actually here almost this term, actually we write here only this term 8 is the value only function of R. Here 8 is the minus del V del R, is a function of R. So we get this. Then R theta generalized coordinates and kinetic energy T equal to half m V square is equal to half m R dot square plus R theta dot square. And so Lagrangian L equal to T minus V, so half m R dot square plus R square theta dot square plus K by R. And the conjugate moment of PR equal to del del R dot L, this is equal to m R dot, and P theta equal to del del theta dot L, m R square theta dot. As the central force is conservative in nature, then the Hamiltonian A is equal to P plus V is the total energy, and is given by value of T and plus value of V. Value of V is minus K by R. So A is equal to this K by R. Actually, this is equal to K by R. P by R. The Hamiltonian canonical equation of motion give R dot equal to del del PRH, and this equal to PR by N, and PR dot equal to minus del del RH. So this equal to, expression is this. And theta dot equal to del del P theta H is equal to P theta by M R square, and P theta dot equal to minus del del theta H is equal to 0. So this is the canonical form, canonical equations, Hamiltonian canonical equations equal to this. Note P theta dot equal to 0. This last equation this. So derivative of P theta equal to m r square theta dot. This the P theta is this m r square theta dot. So m r square theta dot is constant, say L. Hence the angular momentum m r square theta dot of a particle moving in central force field is conserved, and hence r dot equal to PR by m. And this implies differentiating with respect to t, mr double dot is equal to pr dot. This implies mr double dot equal to this, and this using the above relation, the value of this theta dot square from the previous relation, this and theta dot is equal to L by mr square. So mr double dot equal to minus L square by mr r cube minus k by r square, and this is the equation of motion for r. Actually, in this question, we have to find the write down the expression for the Hamiltonian system and derive the Hamiltonian equation of motion. So we have to find Hamilton H, and the canonical equation of motion is this. And this. 4. Next question. Question C. A particle of mass in sorry. Next question. Question D. If the Lagrangian L0 equal to half in ddt q whole square minus half in omega square q square of a dynamical system is modified to L equal to L0 plus alpha q and ddt q, then so that canonical momentum changes, the equation of motion does not change. Here L0 is equal to 1 is equation 1, and L equal to this L0 plus alpha q dot. Q dot means dt of q. So L0 is this 1. So L equal to this. So we have two Lagrangian. First L0 and then L. Let P0 and P be the corresponding canonical momenta for L and L0 and L corresponding to generalized coordinate Q. So P0 equal to del Q dot L0 and this equal to MQ dot, equation 3. And P equal to del Q dot L. So this equal to MQ dot plus alpha Q, equation 4. Obviously, this P equal to P0 plus alpha Q. And this shows that the canonical momenta P changes because P0 momenta for L0 and P is momenta for L. So obviously, this expression 5 shows that canonical momenta changes. The Lagrange's equation of motion for L0, ddt of del q dot L0 minus del q L0, this. So we get mq double dot plus m omega square q equal to 0, equation 6. And Lagrange's equation for L, ddt of del q dot L minus del q L equal to 0. So we get m q double dot plus m omega square q equal to 0, equation 7. And this, notice that these 6 and 7 are identical. Hence, the equation of motion does not change for L and L0. Next question, question E. State Hamilton's principle, derive Hamilton's principle from D'Alembert's principle. Hamilton principle, this variation principle, the motion of a monogenic system, monogenic means holonomic and conservative, and so. For time t1 to t2 is such that the line integral I is the action integral, integration t1 to t2 L dt has a stationary value, that is extremum, for the actual path of the motion. Alternatively, the variation of the line integral I for the fixed times t1 to t2 is 0. That is variation delta I equal to delta integration T1 to L dt equal to 0, where L q dot T is the Lagrangian of the system and T is the Q1 Q2 Q and generalized coordinates, n generalized coordinates, and q dot is the n generalized velocities Q1 dot Q2 dot Qn dot. Now the derivation of the Hamilton's principle from D'Alembert's principle. Fi vector is the force on the ith particle of mass mi. Then the Fi vector equal to mi ri double dot. Ri vector is the position vector of the ith particle. From D'Alembert's principle, summation of I equal to 1 to capital N is the number of particles in the system. If I minus pi vector dot delta Ri equal to 0, the virtual displacement delta Ri is summation I equal to 1 to capital N if I vector dot delta I equal to summation over I equal to 1 to N pi dot vector dot delta I, expression 1. Now pi dot vector dot delta Ri vector, this equals to value of pi dot delta Ri. So we get a ddt of m Ri dot delta Ri, and this expression can be written as this ddt of m Ri dot delta Ri minus m I Ri vector dot ddt of delta Ri. And so we can interchange this ddt and delta this because this because the delta variation in the velocity corresponding to the virtual displacement delta I is given by delta ddt Ri vector equal to delta Vi. So this Vi vector at the position Ri plus delta Ri minus Vi vector at the point Ri. So ddt of this because velocity of this, so position vector derivative with respect to time, and this velocity for the position Ri, so ddt of Ri. So this is the ddt of delta Ri. Also delta Ri dot square, this is the delta Ri dot square equal to delta Ri dot delta Ri dot. this is equal to 2 Ri dot delta Ri dot. This this into this delta Ri plus this into this delta Ri. So 2 into this, 2 into Ri dot delta ddt of Ri vector. So we get expression this. Also, this hence the equation 1 becomes put these values of pi dot and delta I dot in 1, and we get the expression is this: summation of I equal to 1 to n if I vector dot delta I is equal to ddt of this plus delta into this. And if the forces are conservative, so if I vector equal to minus grad I vector this v, so this equal to minus del xi v I cap minus del y I v j cap. This notation I for I particle, and this I cap is the unit vector along x-axis. So del y I v j cap minus del z I v k cap, and v is the potential the function of the system. And the virtual work done, this summation of I equal to 1 to capital N. If I vector to delta I, and this equal to, we get this, so this equal to delta V. Now, T is the kinetic energy, so this equal to T, and the equation 2 becomes, this minus delta T equal to ddt of this minus delta T. So ddt of this equal to delta T minus T. And integrating 3 from T equal to T1 to T equal to T2 with the condition that delta Ri T1 equal to 0 equal to delta Ri T2 at the end points of the path, this variation in Ri is identical, and the actual path and other path. And so integrating, we get summation of I equal to 1 to n if I mri dot delta I T1 to T2 equal to integration T1 to T2 delta T minus VDT. So this equal to 0 because of this equal to 0, delta I at the endpoints is 0, so this expression is 0, and this, so delta integration L dt equal to 0. Actually, delta T minus V dt equal to delta integration T minus V dt. Actually, this expression is delta T minus V dt equal to delta T minus V dt plus T minus V delta dt. Actually, delta variation, no time variation, so this equal to 0. So we get this. Hence, from 3, delta of T1 to T2 L dt equal to 0, and this is the Hamilton's principle of variation principle. And this PDF of this note is given in the description box, and thank you for watching this video.